talk about sound, specifically instruments. Sound. And what I want to talk about is resonance and standing waves. Resonance and standing waves. So, first thing we'll talk about is a string, okay? An instrument with a string on it, okay? And when you pluck the string, what ends up happening is you get standing waves in the string, which mainly ring at the fundamental frequency, right? So this is the length of the string, okay? We'll have an antinode in the middle, and we'll have a node and a node, okay? In the same string, acting along here at the same time, you will often have some overtones, okay? Or higher level harmonics, if you want, is the other thing that we might call this, okay? And these are kind of resonating along with the fundamental, okay? These overtones, right? So this is the first overtone, or if you want, we call this the first harmonic, okay? The second harmonic, and the third harmonic. And what we're going to look at is how do these relate mathematically and how do they relate musically to one another. Music has a very mathematical kind of underpinning, okay? I didn't draw that very well, but hopefully you get the point. This is a takeoff from our standing waves in strings, okay? So this might be, if you plucked a guitar string, what you would see if you could really slow down time. You could see these overtones, or you could see these fundamentals and overtones happening, okay? So something to remember here, right, is if we look at what a full wavelength looks like, okay, if this is the length of the string here, okay, essentially we have length being equal to half of a wavelength, or a wavelength equal to twice the length here, right? One full wavelength would be the continuation of this out to here. The second harmonic, or first overtone, depending what you want to call it, is when the wavelength is equal in length to that. And then we have, here we have the length is equal to 1 1/2 wavelengths. Okay, so we have these kind of options going on in a stringed instrument. You know, the different sounds you get in a guitar versus, say, a violin often has to do with what types of overtones are going on, plus the resonance in the air chamber inside the instruments, which we'll get into later. But you can play the same note or the same frequency if you want on any instrument really, and you can tell that it's played by a different instrument, usually due to the overtones plus the construction of the sound box, okay? So this would happen at a very specific frequency, okay? Now with a guitar string, in order to play the guitar, we actually vary the length by pressing our finger somewhere along here. So if we were to shorten the length, then the fundamental frequency would be a higher pitch. So the lower down the neck we play, the shorter the string becomes, and the higher the sound the guitar makes, okay? It's very mathematically laid out so that those tones that you get, those frequencies that you get, fall into the range of musical frequencies that have been sort of worked out, okay? So this is stringed instruments, but we also can have something like woodwinds or brass instruments, okay, which work in sort of a different way. And they are either in one set closed tubes, or in another set of instruments, open tubes, okay? So the classic closed tube is the old, you know, the old musical jug, if you want. You've ever seen an old-timey band? Oftentimes someone will be playing a jug, and they'll take their lips, and they'll it's not a chicken, it's a person. And they're blowing air over here, okay? And essentially, what ends up happening is inside the tube, you get this going on. You get a wavelength that essentially has its antinode right at the opening and a node at the bottom. And what this will do, now remember, I'm drawing sound, I'm drawing these as transverse waves, but in reality, it's very hard to draw this, but in reality, these are longitudinal waves, and so vibrate up and down, okay? So up and down. So you want, if you have this happening just right, then the vibration happens right at the mouth of the jug, and you get an amplified tone that rings at a fundamental. Now this is a little bit different than a string, right? So let's just simplify. Here's my open tube, okay? The fundamental here occurs when I have an antinode right here. Now how much of a wavelength is this that I've drawn here? Here's a whole wavelength, right? How much of this do I have? Not even. No, half would be to here, right? A quarter. So we can actually get the fundamental in a closed tube when the length and 1/4 of a wavelength are equal. This will cause amplification in sound. If I were to put a half wavelength in there, I would get no sound, right? Because I'd have nodes at either end, and these nodes cannot broadcast sound into the air because there's no movement at a node, okay? So when would the next possible tone happen in a closed tube? Well, it would happen when you're open here, still have a node at the bottom, and you're like that. So how much of a wavelength is that? Well, it's not half, it's quarter plus a quarter plus a quarter. It's when all of this is in there now. So 3/4 lambda, okay? So this is the fundamental for a closed tube. Or if you want the first harmonic, that's another name for it. And this is the second harmonic. And if you want to get crazy, we can even find the third harmonic. Which will come at 1/4 lambdas. Okay, so there's the third harmonic. And you could just continue on going up. 1 3/4, 2 1/4, and so on. And last but not least, what if your tube is open at both ends? By the way, what instruments are like this? Well, there's the jug, but that's not really a real instrument. Can you think of one? A flute. Yes, I believe a flute does count. I think it does. I think a flute does, because I think it's got, essentially, it's closed on the back, open on here. It does have the mouthpiece, right, that you blow wind over, but I think that does just set up the sound like this. So a flute is a good example. What about an oboe? This thing, or a bassoon maybe. Is that what it's called? This thing that stands up like this. A bassoon, yeah. Ah, okay. Yeah, this thing, where you blow onto this little pipe here, okay? And then open tubes. Tubes open at both ends, okay? They're a little bit different. They do this. So in order to have a standing wave inside of here, you have to have this going on. This is how the fundamental works here. Now if you look, if this is a whole wavelength, right? Yes, this is now open at both ends, like the pitch pipe there, like the twirling pipe. So this is actually a half wavelength. So you get the fundamental when the length of the tube here is equal to 1/2 of a wavelength. Now where does the next one happen in your open-ended tube? It happens when you have this. It turns out that's a full wavelength. Okay? And it just continues the pattern.
Scott Boyd Soccer, Young Gate tomorrow at 3:30 U of M. You need to be there by 2:45. Boyd Soccer, you must be U of M. by 245 tomorrow for your neighbor.